unveiling the mysteries of 3I/Atlas. The anti-tail jet and rotation anomalies. The interstellar object 3I/Atlas has captivated the scientific community with its peculiar behaviors since its discovery. In particular, the periodic wobble observed in the anti-tail jet during July and August 2025 has spurred new discussions and raised fascinating questions about the dynamics of the object. The periodicity of this wobble, along with the new insights gleaned from high-resolution images taken after its perihelion, has highlighted an unprecedented anomaly, further complicating the already mysterious nature of 3I/Atlas. The initial observations made during the summer of 2025 indicated a wobble in the anti-tail jet of 3I/Atlas, an anomaly that suggested a unique alignment of the nucleus's rotation axis. The anti-tail, which is a narrow linear feature extending in the opposite direction of the Sun, exhibited a periodic wobble, and as a result, it was found that the jet base was offset by less than 8 degrees from the poles of the nucleus's rotation axis. This remarkable finding implied that as the nucleus of 3I/Atlas spins, the jet precesses along a cone surrounding the axis of rotation. In simple terms, the entire comet is wobbling in a way that suggests a regular but subtle motion of its tail, which makes it even more challenging to understand how such phenomena could occur in an interstellar object. The unlikely alignment and the nature of the jet, what makes this anomaly particularly intriguing, is the suggested geometry of the anti-tail and its connection to the rotation axis of 3I/Atlas. The current alignment of the comet suggests that it maintains a steady day side and night side when it is far from the Sun, and these roles switch at perihelion. During its approach to the Sun, the rotation axis of 3I/Atlas is almost perfectly sunward. This alignment of the object and its interaction with solar radiation is crucial to understanding the behavior of the comet's jet, which is likely connected to a natural pocket of ice inside the nucleus that sublimates under sunlight. However, the real question arises from the rarity of this alignment. The probability of the rotation axis aligning within 8 degrees of the Sun at a heliocentric distance greater than 5 astronomical units is exceptionally low, just 0.5%. This statistical rarity suggests that, without this alignment, the anti-tail jet would have deviated more sharply from the rotation axis, producing a larger wobble in the position angle of the jet. More critically, it could have resulted in the appearance of gaps in the activity of the jet, as its base would have moved between the day side and night side of the nucleus, as 3I/Atlas continued its orbit. Thus, the alignment of the anti-tail jet to the rotation axis becomes an important piece of the puzzle. When these factors are combined, it becomes clear that 3I/Atlas is behaving in ways that no one would expect from an interstellar object passing through our solar system. Post-perihelion observations. A new anomaly unfolds the revelation that 3I/Atlas continued to show a prominent anti-tail jet after its perihelion on October 29, 2025. Added another layer of complexity to the object's behavior. In the months following perihelion, images captured by the Hubble Space Telescope, along with ground-based telescopic observations, showed that the anti-tail jet was still directed towards the Sun. This was particularly surprising because, traditionally, once a comet passes its closest point to the Sun, perihelion, it begins to recede, and its jet is expected to become less prominent or even vanish as the Sun's influence wanes. The fact that 3I/Atlas continued to exhibit a jet directed toward the Sun, even as it was moving away from the solar system, went against the conventional wisdom. This observation raised several questions. How could the anti-tail jet remain so prominent despite the receding distance from the Sun? What were the physical processes that allowed this anomaly to persist even in the post-perihelion phase of 3I/Atlas's orbit? Ice pockets near the poles. The key to understanding the anti-tail. One potential explanation for this anomaly involves the possibility of a new pocket of ice near the opposite pole of 3I/Atlas's rotation axis. The comet's behavior suggests that a secondary pocket of ice might have become active after perihelion, resulting in the formation of a new anti-tail jet directed toward the Sun. This hypothesis, which requires a cometary mechanism, offers a possible explanation for the continuation of the anti-tail jet after the perihelion pass. In addition, the pre-existing anti-tail jet that had been observed before perihelion likely became dormant after the comet's closest approach to the Sun. If 3I/Atlas is indeed a comet, this scenario would imply that the ice near one of the rotation poles had been sublimated by solar radiation during the approach, causing a temporary shutdown of the original jet. However, as the object moved further from the Sun, a new active ice pocket near the opposite rotation pole began to sublimate, creating a new jet that extended in the same direction as the Sun. This complex, dual-pocket ice hypothesis introduces a remarkable feature into the story of 3I/Atlas. The alignment of these ice pockets in such a way that one would be on the day side when the comet approached the Sun, and the other would be on the day side after perihelion. This alignment has an incredibly low probability of occurring naturally. The likelihood of such an alignment is estimated to be just 0.0000025. The fact that this alignment is being observed in 3I/Atlas makes it one of the most significant anomalies to date in the study of interstellar objects. The role of precession and collimation in the anti-tail jet. Another extraordinary aspect of the anti-tail jet of 3I/Atlas is its tight collimation, extending out to distances of 500,000 kilometers from the nucleus. Despite the solar wind and radiation pressure acting on the jet as 3I/Atlas recedes from the Sun, the jet maintains its sharp, narrow structure, which is unlike what would be expected from a typical comet. Normally, solar wind and radiation would have a tendency to broaden the jet, pushing away from the Sun, but 3I/Atlas's anti-tail remains remarkably collimated. This raises several intriguing questions regarding the properties of the jet material, its speed, and its mass loss rate. At present, the exact mechanics behind the collimation of the jet remain unclear. However, the next step in studying the anti-tail jet will likely involve detailed spectroscopic observations of the material in the jet. These observations may reveal crucial information about the composition of the jet and provide insights into how such a narrowly collimated jet can persist over such vast distances. Understanding the material properties of the jet, including its speed and the rate at which mass is being lost, will be vital for refining our theories on the nature of 3I/Atlas and other similar interstellar objects. The rotation period and centrifugal forces, in addition to the anomalous behavior of the anti-tail jet. The rotation period of 3I/Atlas also plays a crucial role in understanding its dynamics. Based on the observed periodicity of 74 hours in July and August 2025, it is suggested that the rotation period of the nucleus is approximately 48 hours. This is consistent with earlier findings derived from periodic brightness variations, which indicated a rotation period of around 16 hours. Although this value might seem typical for a cometary nucleus, it is important to consider the effects of rotation on the surface of 3I/Atlas. For a nucleus with a radius of 2 kilometers and a rotation period of 5 hours, the centrifugal acceleration at the surface of the object is extremely low. The centrifugal acceleration on 3I/Atlas's surface is just 0.0025 centimeters per second squared, which is minuscule compared to the acceleration due to gravity on Earth. To create artificial gravity equivalent to 1 g, the rotation period would have to be drastically reduced to just 5 minutes. Implications for future exploration. The study of 3I/Atlas offers an invaluable opportunity to explore the mysteries of interstellar objects. As we continue to observe and analyze 3I/Atlas and similar objects, we may be able to unlock new insights into the nature of comets, ice pockets, and even the broader dynamics of our solar system. The persistent anti-tail jet, the remarkable alignment of ice pockets, and the odd behavior of the object as it recedes from the Sun are all compelling mysteries that will likely keep scientists busy for years to come. In conclusion, the anomalies associated with 3I/Atlas are a testament to the complexity and unpredictability of interstellar objects. The behavior of the anti-tail jet and the rotation dynamics of a nucleus pose numerous challenges to current models of cometary activity, and the chances of finding similar objects with such intricate features in the future are slim. As technology improves and more detailed observations become available, we may yet uncover the secrets that 3I/Atlas holds within its icy nucleus. For now, 3I/Atlas remains an extraordinary object, and its study continues to inspire awe and wonder in the scientific community.